We've put in a lot of time and effort into defining integrals, learning how to calculate them, and when we can't calculate them, to estimate them numerically using the various methods we discuss. Now it's time to get some use out of all that work that we've put in. In this lecture, I'm going to show you how to calculate the length of different curves. So if you walk along a certain curve, how far must you walk if that function is defined explicitly? Let's say like y equals sine x or y equals x to the 3/2 or whatever. Once we do that, then we shall learn how to deal with functions that are not defined explicitly in the form y equals, let's say, sine of x plus x cosine x, but rather implicitly. We shall then also learn how to do implicit differentiations. But let's begin with curves. Let me give a precise definition of the length of a curve. Suppose that we in 2 dimensions, this is the x direction and that's the y direction. Suppose that we start walking from some point A and end up at some other point B. So we can go straight, or we could go up, come down, go up, come down, and eventually end up at B. And provided A and B are different points, this is what is called an open curve. On the other hand, we could have started at the point A and walked around and eventually come back to the same point, and that's a closed curve. Let's take a segment of any of these curves. So here are 2 very close points, this and that. In order to get from here to here, I could walk delta x in this direction and delta y in this direction. So that's delta y, that's delta x. On the other hand, this delta L over here is a straight line that connects the point here and the point here. This is not the same as the actual distance along the curve, but they're very, very close to each other. So delta S, which is the actual distance, will be close to delta L as delta x and delta y become smaller and smaller. Now, by Pythagoras' theorem, we can see that delta L is then square root of delta x squared plus delta y squared. And if we like, we can take delta x out of this, and inside there will then be 1 plus delta y by delta x squared. Imagine the situation where delta x and delta y become very, very small. In that case, delta y by delta x will tend to dy by dx, that is to say the derivative of y with respect to x. We could also have written delta s or delta L equivalently as delta y square root of 1 plus delta x by delta y squared. And in that case, delta x by delta y would tend to dx by dy. But let's now add up the little infinitesimal parts to get the total length of the curve. Now suppose we want the length of this curve, which is given in red, from x1, y1 up till x2, y2. In other words, we want to know how long this journey is from x1, y1 to x2, y2. And the way that we'll do it is we'll break this up into segments. Let's call that delta S1, delta S2, delta S3, delta S4, and delta S5. Now, obviously, the total distance that will be traveled will be delta S, which is delta S1 plus delta S2, and so on until we reach delta S5. Now, these are just 5 segments, but if we were to take many segments, in other words, if the segments were to become infinitesimal, then this would tend to the integral or the sum of ds, of the small ds's. Okay? So that's going to be the total length. That's the distance that you and I would actually have to walk along this red line over here. Now, we can write s in 2 different ways. We can write s as the integral of dx, square root of 1 plus dy by dx squared, and x goes from x1 all the way up till x2. And so here I am using this formula, and assuming that we've taken the infinitesimal limit. On the other hand, we could have equivalently this formula, dy from y1 up till y2, but here the only difference would be 1 plus dx by dy squared. Now both of these, this and this, are completely equivalent, but here we're taking x as our variable, and x goes from here up till here, so x1 to x2. On the other hand, we could take y as our variable and make y go from y1 up till y2. Let's now apply the length formula that we've just derived to find the length of the curve y equals x to the 3 over 2 from x equals 0 to x equals 1. It's always a good idea to plot out your curve. So we start from here and we end over here. Let's first calculate dy by dx, and that's trivial. That's 3 over 2 x to the power half. We shall need square root of 1 plus dy by dx squared, and that is clearly the square root of 1 plus 9 over 4 x. So the length that we need, let's call that s, is the integral over x from 0 to 1 of this thing here, square root of 1 plus 9 over 4x. There are many ways to do this integral, but simply put u equal to 1 plus 9 over 4x. That's a change of variables. And so du becomes 9 over 4 dx. Let's put that in here. So we have 4 9ths outside, and here we have the integral over u of u to the power half. The only thing that we need to know now are what are the limits of integration. When x is 0, then obviously u is 1. When x is 1, then u is 1 plus 9 over 4, which is 13 over 4. And so this becomes 4 9ths of 2/3, and here we have u to the 3 over 2 evaluated between 1 and 13 by 4. Let's put that in, and this is 8 over 27. Inside we shall have 13 over 4 to the power 3 over 2 minus 1. I'll now look at my calculator and work this out, and what I find is 1.439, and that's it. So that says that if I walk from this point all the way up till this point over here, then that's the length I will travel. And just for comparison's sake, suppose I'd walked on a straight line, and this straight line then of course would be the hypotenuse of a triangle with length 1 and 1, and so this over here would be square root of 2, which as you know is 1.414, etc. So, had I walked on the straight line, I would have traveled a shorter path, but that's something that we already know. I'm going to do a problem that is so similar to the one that I just did that you'll probably ask, why is this being done here? Earlier I had done y equals x to the 3 over 2. Now I'm just doing x to the 2 over 3. But you will see why this is necessary. That's because if I take dy by dx, that is 2/3 x to the minus 1/3. Now when x becomes small, becomes 0 in fact, dy by dx becomes infinite. So if you draw the graph, this is what you get. You see that as x becomes smaller and smaller, y is fine, but dy by dx becomes infinite. This slope here has gone all the way up to the sky. So, if one was to take this thing, square root of 1 plus dy by dx squared, that would give us 4 over 9 x to the minus 2/3, and that's not a good integrand to have. Let me just compare with what we had earlier. So we had y equals x to the 3 over 2. The two functions are the same, obviously, at x equals 0 and at x equals 1. But now the formula that I'm going to use is going to be slightly different. I'm going to write x equals y to the 3 over 2, in which case what I have for dx by dy is, as before, 3 over 2 y to the half, and that means that the square root of 1 plus dx by dy squared. So I'm going to use the second formula that I had derived. This is square root of 1 plus 9 over 4 y. And so what we want is s equals integral over y, and y is going from 0 up till 1, and here we will have square root of 1 plus 9 over 4 y, but this is exactly the same integral that we had before. So therefore the length of this line, this one over here, and the length of this line over here are exactly the same. Here is a problem that will have a slightly different twist to it, because we will not be able to do the integral that's needed exactly, but we shall do a numerical estimate of that. Here is the curve that we are asked to look at, y equals sine x minus x cos x, and we need the length of the curve between 0 and pi. Okay, so it's always a good idea to plot the curve. Here it is. So at x equal to 0, y is 0. At x equal to pi, you see that y is sine pi, which is 0, minus pi into cos pi, which is minus 1. And so here is pi again. Hence we have a picture of this curve. Now, let me take dy by dx, and that's cos x minus, when I differentiate x, I get 1, so minus cos x. And then when I differentiate cos x, I get minus sine x, so I have plus x sine x. And what that means is we've got a simple answer, x sine x. But what we need is the integral of square root of 1 plus x squared sine squared x from x equals 0 up till pi. What's inside the integral, in other words the integrand, is also a good idea to plot out, and it's a nice smooth function which looks like this. Unfortunately, in spite of this being so nice looking, it cannot be integrated exactly. On the other hand, if you put this into a numerical integration program onto a computer, the answer turns out to be 4.698. Well, let's see what we get by using Simpson's rule. So Simpson's rule, which we covered in one of the lectures, we shall apply in the following way. Let's just take 3 points here, here, and here. So the function here is here, and let me pass a parabola through these 3 points. It doesn't look as if it's going to be very accurate, but let's see what happens. In that case, if we call this thing over here f of x, what we need is f of 0. F of 0 is 1. We'll need f at pi by 2, and we can easily see that to be, with a calculator, 1.862. And then f at this point will again be 1. So f at pi is again 1. Simpson's rule says give the first point 1/3 weightage. Then the second point has to be given 4/3 weightage. The last point again 1/3 weightage. And of course we've got to multiply by the grid spacing, which is pi by 2. If you do that, then the answer comes out to be 4.947. So compare this with the exact answer, which is here, or very close to the exact answer, and you see that we haven't done too badly. This was for n equal to 3. We made use of the function just at this point, and this point. Okay, what if we use n equal to 5? In that case, the grid spacing will be halved. So we have pi by 4, then 1/3 of f of 0, and then 4/3 of f at pi by 4, and then 2/3. And here it's f of pi by 2, then again 4/3 f of 3 pi by 4, and finally 1/3 of f of pi, which is 1, of course. And if you work this out, then what you get is 4.731. Now that's closer to here, to the actual answer. But in any case, we've done what we've been asked to. Of course, if you take more and more points, you're going to get closer and closer to 4.698. Next, here's a question that's going to require some thought. We're asked to find the length of the curve x equals integral 0 to y of square root of sec to the 4t minus 1, and y goes from minus pi by 4 to plus pi by 4. Now, this is not of the form that we've seen earlier. We are not given, for example, that y equals f of x or x is equal to g of y. Instead, we're given this rather peculiar thing. However, one thing that we note is that dx by dy is the square root of sec to the power 4y minus 1. And here, just to remind you, in this box is what we had discussed some lectures ago when we first talked about integrals. If you take the derivative of, let's say, f of t from anywhere, doesn't matter what the lower limit is, but if the upper limit is x, then this is f of x. And we had proved this. Now, What we need is the square root of 1 plus dx by dy squared, and that is obviously square root of 1 plus sec to the power 4 y minus 1, and that is 1 over cos squared y. What we need for the length is then the integral over y from minus pi by 4 to plus pi by 4 of 1 over cos squared y, or sec squared y in other words. And you remember that if you differentiate tan y, you get sec squared y, or 1 over cos squared y. We take the limits between minus pi by 4 and plus pi by 4. At the top it is 1, at the bottom it is minus 1, and so the answer is 2. That's the length of the curve. In this case, it was too messy to plot out x as a function of y or y as a function of x, but that's the right answer. Before coming to more uses of the length formula, I'm going to discuss implicit functions. Now, implicit is the exact opposite of explicit. Explicit functions can be written in the following form. Y is some function of x. And we have many examples that we've encountered. So for examples, y is equal to sine x divided by x squared plus e to the x would be an explicitly defined function. Give a value of x and out comes a value of y. On the other hand, one can have functions that are defined implicitly. So for example, if you have x squared plus y squared equals, let's say, 3. In that case, giving a value to x will give a value to y, and correspondingly, giving a value to y will give a value to x. So more generally, if I have something like this, f of x, y equals 0, where f is some function that depends upon both x and y, we say that then y is defined implicitly as a function of x. So let's take yet another example. If you have x cubed plus y to the 7th plus 9x squared y squared minus 3 equals 0. I don't think it's very easy to find y as a function of x. It's going to be very hard, in fact. Or to take yet another example, suppose sine of xy is equal to y cubed. Well, what is y as a function of x? Again, very hard to say, because for this we have to be able to solve the equation y in terms of x. In general, it might be hard to find y as a function of x, but it might still be very easy to find dy by dx. All we need to do is assume that y is a differentiable function of x. In other words, you can take dy by dx. And so, for example, if I have a function like this, sine of y, and I take the derivative with respect to x, well, that by the chain rule will be just cos y into dy by dx. Now let's work out examples in which functions are defined implicitly. As a first example, let's look at x squared plus y squared equals 1. We asked to find dy by dx at any point xy that lies on this curve. So take the derivative d by dx of x squared, then d by dx of y squared, and that must be d by dx of 1, which is 0 obviously. So we have 2x plus 2y dy by dx equals 0, and that's dy by dx equals minus x over y. I call this a curve, but it's a very simple curve. Let's see what it represents. So if this is the origin, this is the point, let's call it x, y. In that case, this is x and this is y. Their hypotenuse has to have value 1 because x squared plus y squared is 1, which means that this is a point that lies upon a circle, and so the curve is actually a circle. Now, look at this formula over here. Let's see if it's telling us the right things. When x is 0, dy by dx is 0. And yes, when x is 0, which is over here, then the curve is flat here and it's flat here. On the other hand, when y is 0, such as over here or over here, then dy by dx is infinite. A second example. Here again, there is an implicit definition of the function y. Let's take the derivatives. So d by dx of x squared, and then d by dx of xy cubed. That has to be equal to the derivative of 1 plus the derivative of x plus the derivative of y. And so that's telling us from here that 2x plus y cubed plus 3xy squared dy by dx has to equal to 1 plus dy by dx. Now, let's take dy by dx common over here. And so we have 3xy squared minus 1 equals 1 minus 2x minus y cubed. And so we found dy by dx from this implicit equation. It's just 1 minus 2x minus y cubed divided by 3xy squared minus 1. And so you see how easily we've been able to find dy by dx, although to have found y as a function of x would have been very difficult here. Let's now return to the length formula that we had derived earlier and apply it to finding the length of the curve, or rather the circle, x squared plus y squared equals 1, with x being in this range. The first thing we've got to find is dy by dx. And again, we've done this, but let's do it again. Differentiate both sides. So we have 2x plus 2y dy by dx is 0. And that gives us, obviously, dy by dx, as before, is minus x over y. What we need is the square root of 1 plus dy by dx squared. And that is the square root of 1 plus x squared over y squared. When we take the common denominator at the top, we get x squared plus y squared equals 1. And so this is 1 over y. Now notice I'm only taking the positive root over here, but we'll come back to that later. So the next thing is to find the integral over x from minus 1 to plus 1 of 1 over y. Now clearly, because x squared plus y squared is 1, and from here y is plus or minus square root of 1 minus x squared. On the other hand, we're looking for a length. A length is always positive, and so we're just going to take the positive root over here. That then gives us this integral. And even though this appears to have a problem at x equals plus or minus 1, in fact, there is not a problem. Let's now look at a change of variables that will allow us to do this problem. Put x equal to, let's call it cosine alpha, in which case dx will be minus sine alpha d alpha. And if I put dx in here, this will give me integral d alpha with the minus sign outside, sine alpha. At the bottom will be square root of 1 minus cos squared alpha, which is sine alpha itself. And so that cancels. The only thing is that we need to know what the limits are. Well, when x is plus 1, then cosine of alpha has to be plus 1, which means alpha has to be 0. And when x is minus 1, then alpha should be pi, because cosine of pi is minus 1. So this integral then is just the integral from pi up till 0, and that is equal to pi. Let's see physically what has happened. So here is our circle. We've gone from x equals minus 1 to plus 1. In other words, we've traversed one of these branches of the function, and this length over here is pi. On the other hand, we could have gone the other way, and that too would have been pi. So going on top gives you pi, and going the other way, this way, would also give you pi. These lengths, of course, are the same. If you were to go all around the circle, that would give you the circumference. That would be 2 pi. In this lecture, we learned how to calculate the distance that we must walk along a particular curve. And we did several examples, both for the situations where the curve was explicitly given or defined implicitly. However, this is all one dimension. A curve involves just one variable changing along it. In the next lecture, we shall learn how to use the tools of integral calculus we've learned to calculate areas and then volumes. That'll be in the next lecture.